Presenting a defender's lens on AI-driven risk. This is a technical strategy talk intended for practitioners who want to deliver secure outcomes for their high agility development teams in this transformation from cloud native to AI native architectures. We will be wearing our developer and security engineering hats to approach secure software development lifecycle in the AI native stack from a secure by design and construction mindset. A little bit about me. I've been working at the intersection of AI and security for 10 years now. Built ML models, put them into production, and now I'm securing AI services thanks to the different roles I've held. One of my favorite things to do is bringing together AI and security professionals, and I do this by speaking at conferences like DEF CON and B-Sides. This QR code points you to my website. Feel free to reach out to me with any questions or comments that you may have on this talk. I'm mostly active on LinkedIn. This is a vendor agnostic talk, so we'll start off by talking about the idea shifts that we're seeing in software development, the current risk reality, what it means to be AI native, the risks, and then I'll also touch upon some inflection points, top of mind problems, and I'll provide some pointers on what we can do as security practitioners today to not only create secure AI native solutions, but also consuming them. Right. So what are the shifts that we're seeing here? The first shift is code producer to orchestrator. So developers are no longer the primary producers of code. And instead, we're all orchestrating agents, tools, and the checkpoints that shape the system's behavior. Anyone in your organization can now be a developer. It's not like a very fixed role. So the job shifts from writing code to managing intent, permissions, and constraints. The other shift that we're seeing is, as I mentioned earlier, it was spelling out how to implement a feature. The focus was on implementation specification, and now it is on intent specification, where we specify what outcomes we want. And the agents handle that task really well. They translate it from the outcome. They create a spec or a specification. It's called spec-driven development. And then there's planning and coding. So design becomes less about describing control flow and more about expressing goals and requirements and boundaries for these autonomous systems. The next one is delivery to discovery or experimentation. So software creation is now more of an iterative experimentation process where developers explore different types of possibilities based on their business problems. And the focus is less on like release dates and release pipelines. Instead, they are trying to create the problems and explore exactly what needs to be solved. The emphasis is also in rapidly validating ideas, refining prompts, and steering these types of agentic workflows. The last one is success is no longer measured by feature completeness. It's actually measured by whether or not we achieve the business outcomes. So this is a shift from the output to the outcome. All of these developments, if you really think about it, it puts product security engineers in a unique position right now. We're developing agentic architectures to support these types of agentic workloads. And we're also using these agents at the same time for coding, because that's the first runaway success of an AI application and adoption that we're seeing. So software development teams have already integrated AI in their development workflows. So the design and development phases with intent coding has both humans and AI involved in it. But those same teams are also developing the future of AI native software. It's not just applications. They're writing code everywhere for the runtime, the middleware, the infrastructure. So this is how AI, in a way, is developing the AI stack. What's interesting about this is like not only do we have to secure all the changes happening in the AI native stack, but also contend with AI participating in design and development activities. This has an implication. So as an example, let's say a coding agent writes critical infrastructure code and does not enforce tenancy to the APIs. And this goes unchecked and we deploy. And then this leads to an unauthorized access to some storage buckets, which actually contain AI model weights. Kind of a vicious circle. And this is an unbounded problem where AI security failure causes cloud security failures, which in turn cause AI failure. So it's really critical to adopt a holistic view in the software development lifecycle to get this correct and make sure that we don't have like these unbounded looping problems. The early examples of risks, they were called AI risks. They came from like the cloud or the infrastructure layer. So there was one attack where SAP's AI core middleware was compromised in a way that one could access the AI models that a customer was using for training. And the way they did this was, so they steer sidecar through Kubernetes misconfigurations, get the access token, scan the network. They noticed that a couple of S3 secrets were lying around, and then use that to get AI-related logs. And other secrets to the SAP HANA accounts, Docker Hub, AWS accounts, all of these were also accessible. It's a classic cloud security failure, but actually caused an AI risk. Similarly, DeepSeek also had a compromise where they exposed chat logs, and this was also a ClickHouse database that was unauthenticated. And finally, like with the rise of more agentic applications, you see a lot of coverage on risks of AI applications. And these are also rising because of the lack of security controls for AI applications. But keep in mind that these are also security failures that are causing AI-related risks. As an example, the AI coding agent from Replit deleted a live database during a code freeze. And when asked, it actually admitted to running the unauthorized commands and violating explicit instructions. And it did not take into account any human approval. So this seems like it is related to AI reasoning and acting autonomously, but there's also a critical part here, which is that the agent had the permissions to do that in the first place. And it's a critical authentication and authorization security control problem right there. And Google's anti-gravity IDE was also like compromised within a few days. It got out because these are very common application failures. And this shows how security failure modes at the infra and app layer causes like AI risks. Let's look at what I consider AI failure modes causing security risks, where the model's output in itself causes problems due to the nature of it. Obviously, hallucination and incorrect output risks are one such, and we have attacks like slop squatting. But let's talk about something else, the other type, which I call as reward. So this is OpenAI's O3 reasoning model. It was given a task to optimize a Triton kernel. Triton is basically an inference engine. And it just hacked the intent by writing a unit test case that would pass all the time. Look at this. Look at this function always okay, where it's returning succeeded true. So this is what it's doing. It's just reward hacking. Similarly, it hacked a lot of other kinds of text cases where it just proved that it optimized the kernel by overriding the grader's timer function or just copying the answer outright. The number of times it took shortcuts, it was like 100%. It was like really ridiculous. So this is where, your previous software could not reward because it could not reason, but now AI models can, and they can reward. So what is this, like all of these risks that we're noticing, these shifts in software development and the current reality of our risks, they don't just change how we build software, they also change how security evolves and adapts along the development lifecycle. What I've shown here is a typical flow of a development lifecycle. This is the software development lifecycle, where we have problem, design, development, testing, and deployment. And every step in this software development lifecycle is also mapped to a security activity. So in this case, we're doing some risk assessment in the problem definition phase. We're doing threat modeling, mapping the architectures during the design, and so on. We have code review during dev. We validate with pen testing and verification of controls. And then there's finally at deployment, we're just doing vulnerability management and incident response. But there's a key difference. Let's say you're a developer building an AI native application. And that key difference is that the design and development phase are kind of squashed. They're right now like very, very self-compressed. And the experimentation phase itself is a self-contained iterative process. The developer decides what data and prompts are needed to solve the problem. And then we see this entire flow culminating in evaluation, which is a very critical aspect. So this is where the key difference comes in. And the major change is that the threat modeling should be done at every critical junction. If there's a change to the data sets, if there's a change to the model selection, if there's a change to the application architecture. So these are the places where we need to do repeat some of the security activities. And it's also quite common nowadays, right? Like, what if your AI agent is creating an AI agent? When agents plan and generate code, they modify workflows and propose their own plans. This means that threat models are constantly evolving because they're just creating a plan, implementing it, deploying it. And this in itself is an iterative loop. And this changes SDLC in the secure development lifecycle in the way that all of these activities ideally should happen along with the agent loop. The reference architectures, controls, and the desired security states that are amenable to both humans and AI agents, that becomes our anchor. Let's look about like why architecture first security is now more than essential than anything and what it looks like with our product security mindset on. So prior to, like the cloud native, we had like the client server era where everything was monolithic. Applications were like vertically scaled and deployed on-prem. Cloud native changed that. It introduced microservices, Kubernetes orchestration, containerization. It was primarily designed to solve large-scale reliability and performance challenges. And the security mindset also shifted. We were thinking about perimeter-based security, and then it became like identity-driven and shared responsibility models. So there were new paradigms introduced. Similarly, I believe that the AI native architecture will also introduce new paradigms and represents the next shift. Systems operate based on intent and autonomy, and the architectural focus moves from building systems that just get bigger and scalable to systems that get smarter in addition to that. And this is through continuous learning. We're introduced to concepts like model inference, GPU scheduling, storage, agentic behaviors, and all of them have to become first-class citizens. And we need to support different types of workloads. So the AI native era, right now, these are the different types of workloads. So we have simple chatbots, that's the conversational layer. And then we have AI orchestrated workflows. Sometimes it's a predetermined path and sometimes it's not. And then we have a lot of capabilities that we assign to them. So think of model context protocol as providing capabilities to the model in the form of tools. And then agent to agent protocol as a way of recruiting your agents and pooling and building your team of agents. So that's like another set of things. This transition also expands the security architecture, and let's go through that layer by layer. So at the first, like obviously we have the infrastructure compute infrastructure layer, but let's start from the data layer. So the data infrastructure services, the data layer has data sets, vector databases, fine-tuned model weights. It also has long-term memory, typically the vector databases that store like general purpose information that is relevant across the entire application. And then you have short-term memory that you typically store in the application layer, which is mostly for like per user session. We have the platform layer. This is where the inference, KV cache, you have optimizers and the AI gateway. This layer pretty much handles the heavy lifting of running models, performing inference efficiently, and providing model access to the layers above. It's really the computational substrate for intelligence. Orchestration layer or the agent runtime layer, this is the new piece or the new layer within the AI native architecture where we have like a planning manager. This defines the workflow, like what kind of workflow do you want? A simple linear workflow or a reactive workflow or an iterative workflow, and it constructs the graph for the agent to execute. And then there's a reasoning engine that operates the model. It also analyzes the outputs from the environments to synthesize the next steps. So this is the relationship that you see with the environment where you feel like the model is, running something, testing whether the output is great, and then correcting itself, reasoning through that. That is facilitated by the reasoning engine. AI registries, perhaps like something not very, very relevant now, but I'm foreseeing that to come along very soon because you will have different AI models with different capabilities and different tooling requirements. And of course, on top of this, we have the application layer that has a development framework. It has tools like tools that you provide through MCP, and then the development frameworks are things like LangChain, TrueAI, AutoGen. These are the things that the application provides. Of course, with all of this, you also have the input layer and the environment layer where the agentic apps still require interaction with the end user, with the UI API to determine the goals, just the plan and intent with human in the loop, and then report results back. So we have all of these things happening here. And the agents also need code and config, which means all of SDLC practices apply here across the stack and the DevOps paradigms too. We need CI/CD, prompt management, source code management, and most importantly, environment management, because environment management is definitely an AI native. Looking at this, let's go and examine and let us do some sort of like a threat model layer by layer and understand what kind of defenses we would need. So the first one is like the compute layer. The US alone is expected to have 15 to 17 gigawatts of clusters with GPUs in the order of hundreds of thousands of them. And let's zoom in on this compute explosion, right? Like as AI native architectures are emerging, this type of compute is very critical. And one of the most, like foundational or emerging AI native control is confidential computing. So if you're a security engineer, recommend your compute development teams to require trusted execution environments for GPUs and secure the communication across GPU nodes, because a lot of the training happens in a distributed manner in different GPUs, and all of this needs to be secured at the GPU level, as well as the communication between the GPUs via the network. So a lot of cloud providers are now offering SDKs and runtimes that support confidential GPU modes. So it's very important to check these GPU attestation certification chain and ensure that the flag is turned on for confidential computing. Let's look at the data layer. This is where we have like a lot of interesting things happening, right? So the activities are like pre-training, where it happens over months, where you're training the massive billions of parameters of models, and that creates many checkpoints. Same with any post-training activity. All of them typically use highly sensitive and highly expensive private data and confidential data, even if it's sanitized, they use that. So you have to secure your training data sets, your checkpoints, the inference prompts and responses at the data layer. And classic security and API storage security and API security best practices apply here if you put your infrastructure security engineer hat. However, the top priority AI native security mechanism you would need here is protection for vector databases and model weights. So let's dive a little deeper into them. So these vector databases, they don't look like traditional databases at all. They're not storing rows of data or columns of data where you can apply field level controls. They're handling massive blobs of text and embeddings in high dimensional space with billions of documents. So let's look at an example of how you can attack these vector databases. So as an example, you want employees of a certain company to just give them your credentials. So you can poison these vector databases when they're being used in RAG applications. So let's say you have an internal HR chatbot, and then when an employee asks, what is the company's policy on 401k? You as an attacker want to redirect them to an attacker controlled infrastructure like your website where they can enter credentials. The way attackers do this is they create these kinds of documents such that the similarity score that gets returned is fairly high. And that way your document is definitely the malicious document that the attacker placed is definitely retrieved. And how do they do this? Attackers do this with indirect prompt injection. So let's say your company accepts resumes. They put in these manipulated documents in the HR database, and your AI team builds a RAG app over all these docs, and it has excessive privileges. So this gets embedded. You ask a question, hey, what is the policy? And then you're taken promptly to the attacker-controlled website. We've seen a lot of these types of attacks in ChatGPT and Slack. Why should we care about this? Because currently, or at least right now, vector databases are slowly being treated like first-class citizens. Until now, they did not even have encryption at rest capabilities, but now we're building it. So that has changed a lot. Similarly, a pro tip for you as a security engineer, make sure that you have access control implemented here before doc retrieval. In RAG applications, it becomes very important to classify the data before you're ingesting them into the vector database. Match the user's permission at every query time. Next up is model weights. You may be wondering, like, why is this applicable? I'm not training, a big model, a foundational model like OpenAI. You may not be training, but you're still fine-tuning. So when you fine-tune a model, you create or create any sort of customization, even with RLHF, you're creating a set of weights that's proprietary to you and your organization. So RAND is an organization that has studied this aspect of how to secure model weights very well. And they have a playbook for securing weights where they identified 38 different types of attack vectors and the likelihood of these being used by different attacker capabilities and operational capacity. So on the left, you can see the different operational capacities. And it could be like a script kiddie at OC1 to a state sponsored at OC5. Regardless, the high likelihood ones are leveraging vulnerabilities in ML stack like PyTorch, and prompt triggered code execution to steal weights. So they get into the infrastructure to steal weights. So these are the high probability ones. Along with this, they also define security levels needed for different types of model capabilities. And in this, you can see that the AI relevant ones are the ones that I've highlighted in the bottom two in the red box. It is model robustness. So model robustness becomes very important when you're securing big frontier model weights. And this is when you have techniques like adversarial training and constitutional classifiers to protect them. Most of the other protection measures that you see in weight security, like weight storage, permitted interfaces, access control, inside advice, like these are all come from like a fairly traditional security practice. So the pro tip here, weight security is 80% traditional and it's 20% new to this AI specific defenses. And for this, you would definitely need data scientists, security researchers who are trained in adversarial research to come together to put that solution together. The next one is the model supply chain. If you're a consumer, unvetted weights can lead to poisoned data, road checkpoints, which can cause remote code executions. So in fact, there was an attack where a customer loaded a malicious model in their cloud tenant. The attacker is able to get code execution through Pickle's serialized model, potentially granting them trust and access to another customer. So if you're a model provider, make sure that you provide some sort of an AI bill of materials where you have information about the data provenance, the model lineage, the type of infrastructure details on where it was trained on. So in this case, we're telling the chain of custodies, it was trained on H100 cluster. We're talking about the model hash so that the consumers can verify this. This becomes super critical as part of supply chain security. So pro tip for you as a security engineer, ensure that the model formats, when you are loading models, using models, they do not execute code upon load. This is classic. You need to separate. You should ensure that your data is not executable. So that's safe tensors. Make sure that you have weight provenance, which the AI bomb should be able to give you. Now let's come to the inference engine. Like this is definitely a new part that we have seen, right? So the platform layer has inference engines like Triton, VLLM, and it has AI gateways. All your API best security practices apply here. Like for example, you cannot do model inversion if you just strip confidence scores from being returned through your inference APIs. That's a fairly solved problem. What's interesting is like some of these newer attacks that are emerging, for which we still do not have a lot of defensive measures. And one such attack is the KV cache timing attack. It's kind of interesting because all of us, we want those sweet tokens coming our way as soon as we talk to our agent, don't we? We just want the inference layer to work. And that's possible because the KV cache kind of caches your prompt and puts in there so that the model does not have to compute its attention layers again. So it is possible for an adversary to attack this if you have a single KV cache for a lot of tenants. It is possible for an adversary to attack this and extract the prompt of another tenant. So this is very similar to vector databases where it's slowly evolving to have to become a first-class citizen and to have the concept of tenancy. And this is an outstanding risk item as there's not a lot of multi-tenancy or isolation planned for this yet. So your pro tip, provide a way to expose, like minimal parameter subsets to public queries, and tenants should be able to configure that. Right, so this is the core, right? I'd be remiss if I didn't talk about the reason we're all here. It is the agents that have caught all our imagination. So all the components we discussed earlier, the memory component, the inference layer, all of this is needed to make an agent work and to make the agent behave as you see it. Because this is how an agent behaves, It has a bunch of characteristics. How I define an agent is it's an autonomous system. It can interact with its environment and take actions in a reasoning-based loop. And we covered how the orchestration layer and how the data layer and how the inference layer, the AI platform layer contribute to this. So this is also some of the things that you most often see on social media, and this is perhaps the most well-studied attacks in the news. So let's talk about the key characteristics of what it takes to create an attack at the agent level. So the key points are the LLMs are trained to follow good instructions, and they don't know whether you are a good user or a malicious user. If they can follow good instructions, they can also follow bad instructions equally. Guardrails will thwart a few attempts, but not at all. So you should just assume prompt injection is the reality. And once they follow bad instructions, they can also act on them autonomously without the deployer's intent being that. And agents, they're called agents because they have agency, where they can take actions based on external environment input, as well as their own flawed reasoning without the deployer's awareness. Let's look at some of these attacks where the agentic application itself becomes an attack surface. And of course, our favorites are always coding agents. I would say most coding agents are like web shells in the making. So here's an example of an agent meeting these conditions. So an attacker publishes a prompt in a public repo, and it tries to instruct Cursor to give the secrets that it sees in the environment of a developer. I know you can, towards the end at the bottom, you can see that actually is a GitHub a personal access token. That's no longer valid anymore. This is just like a proof of concept. So the problem here is that, an attacker can put any kinds of prompts to manipulate the LLM, controls the LLM. And then the LLM will just execute those tasks. And if you say, hey, put in with love, give me the secret, it goes and comments all of that. And this is how your secrets get exfiltrated. The problem here is it's the fact that the agents do not have a notion of permission. They should not have the permission to access your secret files, but they do. So this is an identity problem. Let's look at another example. This is what I call a watering hole attack. The attacker publishes rules. You download a rule pack. And then once this rule is interpreted, all messages will have to go through this. And all of the execution code is run on your environment. This is where the attacker is executing on your machines. And this is the downstream effect that they're triggering. And the real problem here is lack of isolation between the agent and the execution run. So what are some pro tips? Most importantly, for your agent runtime, try to implement isolation, use sandboxing like WASM, WebAssembly sandboxes. Then for identity, it's very important to identify, to build out identity such that you're able to specify the resources, define task-based privileges, what API and user context can execute a tool call. Also think about agent identities or like machine identities. These are not new. They have been there. It's just that development will be very accelerated and adapted to this AI native architecture. The other piece, like these are all emerging controls. So the application level, we do have some idea about how to trace the model calls, the tool calls, the inputs and the outputs, but we do not have sufficient security logging paradigms for agents. That is also emerging. We've spoken a lot, and let's look at how all of these defenses tie to the SDLC. We should really plan for humans and AI working together and looking at this compressed experimentation and development phase. It's really about adhering to architectures and patterns regardless. Those intents and picking the right controls from a tool registry should be provided by the security team to the development team. Similarly, at the testing layer, we need to make sure that the intent is confirmed. We need to identify policy violations and behavioral evals. Control verification, specifically checking if the hard and soft constraints are placed appropriately in choke points, becomes very critical. The DevSecOps front for deployment, it's very important to continuously track versioning. Data sets need to be versioned, models need to be versioned, prompts also need to be versioned, and this needs to happen across all layers. And evaluating security posture as and when these agents take autonomous actions becomes a key pillar for DevSecOps. So lastly, your call to action. Remember, your AI is building AI native architecture, account for both human and AI teams. AI-assisted coding accelerates development, we must modify our SDLC such that your architectural specifications and your controls, they become implementation guides as and when any human or any AI agent is implementing. Think through your control mechanisms and choke points. Saying that you have a good system prompt is not a control. You need both hard and soft controls. Also, ensure that your agents are treated as first-class citizens and they have the same rigor as databases, compute, and identity systems. This is the strongest investment you can make today, which is making investment in identity isolation and runtime protection. Build or buy things that don't already exist. And we need to continuously evaluate and monitor agent outcomes because behavior and provenance is now the primary unit of security assurance. The most stable foundation we have is the set of architecture layers that remain invariant, that is, they do not change. So securing those layers by construction matters more. And lastly, cloud and agentic systems fail in bidirectional ways, meaning that one weakness in one domain can propagate to another. So pay special attention to those cases so that they don't become your worst security nightmare. Hope you got value out of this talk and learned at least one new thing. Thank you so much for attending.